All right, today we're going to look at how to find an equation for velocity for an object that has fallen off a tall cliff, and we are including the force of air friction. All right, so we know that if there's no air friction, the acceleration is negative 9.8 meters per second squared. So the velocity is going to increase every second by 9.8 meters per second. However, that's an idealized situation. When friction is accounted for, if we look at a graph of velocity versus time, initially the slope will be 9.8 meters per second squared, but over time, the falling object is not going to speed up as much as it did the previous second. And there's some maximum speed that the object can reach called the terminal velocity. So what we want to do is find an equation for this curve right here. And by the way, I'm treating down to be the positive direction, so I'm going to make my velocities positive. Okay, so first off, let's look at force diagrams for the falling object. So when the object is first released, before air friction becomes significant, the only force acting on it is the gravitational force. And if I were to divide this gravitational force by the mass, I would get an acceleration of negative g. Let's come down here a short while later. There is an air friction force proportional to the velocity, kv. So if I look at this, what I know is that the net force acting on this small object is mg minus kv. All right, and again, I'm treating down to be the positive direction. All right, so mg is positive, kv is negative. Now, let's come down here after the object's been falling for a while. So as time goes on, this friction force is going to get bigger and bigger until it becomes the same size as the gravitational force. At that point, the gravitational force and this friction force have the same size. Well, when that happens, the object stops speeding up. It's reached its final velocity, which we call terminal velocity. So I can solve for the terminal velocity here. It's just mg over k. And k is just this drag coefficient, okay? So now what I'm going to do is I'm going to use these things to try to find an equation for velocity here, all right? So at any given point, the net force equals the gravitational force minus the frictional force. Okay, now I'm going to rewrite net force as mass times acceleration. And what I'm going to do is I'm going to divide every term by k. Now, the reason I did that is because mg over k equals the terminal velocity. All right, so on the right-hand side of the equation, I got terminal velocity minus velocity. Now, I'm also going to rewrite acceleration as dv dt. So what we're going to need to do is we're going to need to do some integration to get the equation of this line. And the reason we do that, we have to integrate here, is because the acceleration is not constant. Because the force of friction is changing with time. Okay, so I am going to multiply both sides of this equation by negative k over m. So actually, I multiplied both sides of the equation by k over m. All right, now what I want to do, because I'm going to integrate, is I want to get my dv and my v together. So I'm going to divide both sides of the equation by vt minus v, and I'm going to multiply both sides of the equation by dt. So I have dv over vt minus v equals k over m times dt. Okay, now here's where I'm going to do the negative thing. I'm going to multiply both sides of the equation by -1. All right, so I'm going to rewrite this over here. So I'm going to have dv over v minus vt equals negative k over m dt. All right. Okay, now I'm going to integrate both sides of this equation. So before I integrate, I just want to, so I'll draw my integral sign. So I'm going to integrate from 0 to v for dv v minus vt equals negative k over m. Those are just constants. I'm going to integrate dt from 0 to t. Okay. Now, before I do this integration, I just want to point out that if I have du over u, and I integrate that, this is the natural log of u, all right? So, if I make my u equal to v minus vt, du is just dv, because vt is a constant, all right? So, this is going to equal the natural log of v minus vt evaluated from 0 to v, and then on the right hand side I get negative k over m, and dt, take the integral of that, that's just t. I'm going to evaluate that from 0 to t. Okay, so on the left hand side I'm going to plug in v for v, and I'm going to plug in 0 for v, and I'm going to subtract those two things. So I'm going to get the natural log of v minus vt minus the natural log of negative vt equals negative k over m times t minus 0. Okay. Now there's a rule about natural logs. The natural log of a minus the natural log of b is the same as the natural log of a over b. So I'm going to rewrite this as the natural log of v minus vt over the natural log of negative vt equals negative k over m times t. Okay. Now I want to get rid of those natural logs. So what I'm going to do is I'm going to take little e, the exponential function, and I'm going to raise e to this power on the left-hand side, and the right-hand side I'm going to raise e to this power. So I have e raised to the natural log of v minus vt over the natural log of negative vt equals e to the negative km times t. Okay. Now, e raised to the natural log of x is just x. All right. So on the left-hand side, this becomes the e and the natural log kind of go away. Right? So I'm running out of room here, but I'm going to switch up to here. So I have v minus vt over negative vt equals e to the negative kmt. All right. So e raised to the natural log of x is just x. Now I'm going to multiply both sides of the equation by negative vt. I'm going to add vt to both sides. And I can factor a vt out of the right-hand side. And voila. What I have here is an equation for velocity, and it's related to the terminal velocity of the object. All right? And it's a function of time. This equation right here is the equation of this curve. All right, so let's think about this a little bit. If I make t 0, inside the parentheses, I've got 1 minus e to the 0, which is just 0. So at t equals 0, v equals 0, which matches up. If I make t a very large number, like infinity, e to the negative infinity is 0. So inside the parentheses, I have 1 minus e to the negative infinity, or 1 minus 0. So as t approaches infinity, v approaches terminal velocity, which is exactly what we have here.